Hello, good afternoon or good morning. This is week 14, it's the last week of the semester. So I'll remind you of a few things. First off, there is no final exam in this class, okay? When you finish turning in your last video and your last critical friends notes, then you're finished with the semester, okay? I encourage you, please submit your videos. Okay, that's actually very important because for the physics part of the course, that's all the grade your grade depends upon. I honestly want everybody in this class to do well. I know it's been a very difficult semester, especially for you. And so I just want you to hang in tight, do a good job. If you don't have a long video, never mind, just turn in something that is good, that is appropriate. Secondly, finally, I should say, is whatever's in your box you can keep. I mean, I think that the electronic balance is wonderful, okay? The compass and magnets may be wonderful too, but it's all yours, of course. Okay, so now let's, this week, there's actually a lot of topics here, okay? Let me, let's see, yeah, okay, I think here it is, right? Magnetism, okay? Magnetic induction, magnetic force, electric motors, all of these things. There's a long history to magnetism. Actually, it was discovered by mariners in the Mediterranean who discovered that some rocks called magnetite would orient themselves in one direction, and therefore they could navigate, okay? Even at night, or I should say even in the day with no stars. So, as a beautiful long history, it is electricity and magnetism is the most beautiful theory in classical physics. It's really very, very beautiful. And so, somewhat counterintuitively, I'm going to list the sort of 5 main facts, which may not make very much sense to you, but they will go on to do practical things, okay? So, first off, an electromagnetic wave, which is the way we communicate with sight, with cell phones, with any electronic device. I mean, television signals, radio signals. It actually connects electricity and magnetism directly, and electromagnetic wave is actually oscillating electric and magnetic fields that travel at the velocity of light. Okay. Second point is that if you take a charge and you move it, you produce a magnetic field. So a current in a wire produces a magnetic field. That's called Ampere's law. Secondly, if you take a magnetic field and you change it with time, make it go up and make it go down, it produces an electric field that goes around in a circle around the changing magnetic field. That's called electromagnetic induction. And from that, of course, we get generators, because how all the power arrives in our homes. It's generated by electromagnetic induction. Conversely, in the same way that you can change a magnetic field and get an electric field, you can change an electric field with time. Make the magnetic field, electric field go up and down. It produces a magnetic field that goes around in a circle. So this electric and magnetic fields are very much like each other. In fact, within the theory of electromagnetism, they're really the same. Okay, and then an electric current inside of an electromagnetic field feels a force called Lorentz force, but never mind its name. That force is responsible for how motors work. Okay, and so we'll make a couple of small electric motors. So let's go back now to the simple things here. This is a magnet, and it has a north pole and a south pole. It's called dipole because there are 2 poles, north and south. And if you put it underneath for a piece of plastic that has iron filings on it, the iron filings will align themselves with the direction of the magnetic field. So the magnetic field actually fills all of space and has a direction. And so these iron filings align themselves with the magnetic field. Here's a somewhat cleaner version of the same thing. You have an array of little compass needles, and you can see the little arrows on them. And you put, again, a dipole magnet in there, and all the compass needles line up with the direction of the magnetic field at the location they're at. Here's another one, okay, a different magnet, basically same device, same array of little compass needles. Now this is called a dipole field. You can see little arrows pointing around. I mean that each arrow is the direction of the magnetic field at that point. So you can see the magnetic field starts at the top, it goes around in a big circle and comes back and comes in the bottom. Okay, and that's a dipole magnet. Now actually we live in a dipole field. Okay, here's the Earth. Here's the model of the Earth. On the right hand side, for example, the right hand side is simpler. If the circle there is the Earth, then the magnetic field on the outside you can measure with a compass needle, okay? And it looks as if there's a dipole magnet at the center of the Earth. Well, there isn't actually. There's really churning iron and whatever's going on is actually not completely understood. So there is a geographic North Pole, and you know what that is. That's what appears on all the maps and so on. The magnetic pole is actually 12 degrees off from that. So the magnetism doesn't exactly follow the geography, okay? And indeed, the magnetic pole is actually a south pole. And that's because compass needles point to the north, which means they have to follow the field line, which are going from the North Pole out and around into the South Pole. So at this little location here, that's approximately where Iowa is, or maybe Iowa is more or less up here. So the magnetic field of the Earth kind of points into the Earth, kind of pointing northish, but pointing mostly down into the Earth at the location where we are. Now here's another drawing on the left. Maybe it's not exactly any better. The actual magnetic North Pole actually wanders around for hundreds of miles over a period of 100, 200, or 300 years. It's been measured, of course. It wanders around. So whatever is going on inside the Earth, it's not completely stable. And furthermore, interestingly enough, the magnetic field of the Earth flips every 200,000 years approximately. So something makes the whole thing flip. And I have no even clue how that could possibly happen. But in any case, whatever happens on the inside of the Earth, it flips rather abruptly. Well, the flip takes maybe, I don't know, 1,000 years or 10,000 years or something to manage, but it flips. So, and then, by the way, there are lots and lots of creatures on Earth which navigate using the magnetic field of the Earth. So migratory birds, for example, and also turtles and other animals that depend upon who travel long distances in the sea or over the land. They use the magnetic field of the Earth, and it's been found that they have little magnets in their brains or in their nervous circuits, so they're able actually to detect the magnetic field and therefore follow it and migrate, for example. So here is, for example, a video on that you can do. You have a magnet. You have a magnet, and take a piece of paper, and here's a compass. And so now,
hello. So this is a compass. You should find a compass in your box in week 14 on magnetism, and it's a regular compass. It'll point north. North is the direction you're looking. So if I get this magnet far away and take a look at it, and you can see that it is north, is pointing this way, which is north, okay, at this location. All right. So we can use this compass to measure the magnetic field of a magnet. And this is a permanent magnet. I taped it down so it won't move, but I will untape it and then retape it in place. This is a permanent magnet. It's made out of rare earths from the periodic table. You can look them up on the periodic table. And this is the north side. So I could put an N there if I wanted to. And this is the south side. And so I'll put it down. Oops. I'm using, oops. I want to just tape it so it doesn't move. And okay, so there you go. So now I've already done these blue arrows, and but it should be the same on the other side. But let's just check and see. So suppose we put this compass right here. You can see the north is pointing this way. That's north, that's south. So you just put the compass anywhere you want, anywhere in this field, and then move it aside and draw the arrow. Okay, that's the arrow. That's what the magnetic field is like at this location. Because what it does is the compass aligns itself with the local magnetic field. So this is a north. Oops, see, there's iron in this pen, so it attracts to the magnet. So the North Pole will always point in the direction of the magnetic field. So let's put it out here. So now the North Pole is pointing. Oops, let me get things out of the way here. The North Pole is pointing this way. So at this location, I'll just move it aside, it's like that. And if we put it out here, north looks like that. Okay? And put it here, north looks like it's pointing here. So here it is, okay? So we can just, north is pointing this way, okay? So I did a lot more here, and I'd like you to do this actually on a plain piece of paper. In your notebook would be fine, but the notebook doesn't sit very flat. But in any case, this is the local position of the magnetic field everywhere, and I did many more here. And then you can draw magnetic field lines. So this magnetic field line looks to me like it goes like this, and goes around to here, right? Sure enough, it does. And there's another one that does this, and there's one that does this. Okay, and that is a dipole. Here's the direction of the magnetic field, pointing in this direction. I'll put arrows on it. And so that is a dipole field. It's a dipole field. It has a North Pole here, and the magnetic flux lines leave the North Pole. Whoops. They leave the North Pole, go out and around, and come back to the South Pole. All of them do that. They don't end anywhere else. They end right on the South Pole. So that's a dipole magnet. Now, as we saw in the recorded, as we saw earlier, there is something inside the core of the Earth that makes a dipole field. So the magnetic field of the Earth is a dipole field. And if you're to draw it to scale, you know, this might be about the size of the Earth. This might be about the size of the Earth compared to the shape of the dipole field. And so what's inside of the Earth generating this is actually not truly known, although you can make a lot of good guesses. Okay, so next we will then look at making a motor.
Okay, let me comment at this point. The little neodymium magnets are made out of rare earth elements. And in fact, the Ames laboratory here in Ames, Iowa, is the greatest lab in the world for making rare earths and understanding rare earths. So they're very powerful magnets. If you have two together, they will snap together with such a force that they'll pinch your finger. It'll hurt. Number two, they are bite-sized, and children can swallow them. And a child ends up in the emergency room very quickly because if one of these is in a child's stomach, it will attract to any piece of iron nearby, okay, like the door of the car you're trying to get into. And so the magnet you have is not connected to anything. It's just a simple magnet. I think it's probably connected to a AA battery for making a motor. But it's very important, if you use these in class, and you really should because they're very strong and wonderful magnets, they should be screwed down to a piece of wood. Okay? Now, I have a slightly regret because I don't have, yes I do have, I have a neodymium magnet, but it has a hole in it, you can see. And in fact, it's beveled. It's beveled in such a way that you could put this down on a piece of wood, put a screw through it, and screw it into the wood. Piece of wood can be this big. I mean, the piece of wood can be, you know, yay big, right? And so you can't swallow that. And the magnet itself is screwed into the wood, okay? So that's an important safety feature, okay, dealing with these magnets. Okay, let's go on to look at this. This is actually a coil of wire. So, and this magnetic field, if you cover up what's on the inside and you look at just the magnetic field going out and around and coming back, it's also a dipole field, except it's generated by a current loop. So you can generate a dipole field in two ways. One, with a dipole magnet sitting right here in the middle, or with a current of with a loop of current called a coil. Okay. Now, if you take a lot of these coils and stack them up, one after another, and run a current through all of them like that, you get what's called a solenoid. And a solenoid is a really wonderful field because the magnetic field on the inside are the blue arrows here on this figure, and they're all perfectly uniform. So the magnetic field is the same here as it is here and all the way around on the inside. And all you do is have a coil, just a helix actually, a helix of wire, and put current in it, and you have a uniform magnetic field. Okay, so we won't be doing that, but you know there are a lot of these around actually in the physics lab and so on. So how does a current make a magnetic field? Well, actually, here, this is a single loop, complicated, right? And this is a solenoid. Yeah, okay, so it's uniform on the inside, but you know it's not so obvious how you get a uniform field out of this helical wire. What you start with is the basics. An electric current makes a magnetic field that goes around in a circle. So in this figure here, in this photo, take this. This is actually happens to be a coppered tube. Suppose that there's a current in this piece of copper. Okay. If you put your thumb in the direction of the current in the wire, your fingers are the direction of the magnetic field. So magnetic field are circular lines that go around a current. Okay, and you have to use your right hand for this to get the right answer. Use your left hand, you get the opposite direction. So use your right hand, and that's called the right hand rule. Okay, so thumb in the direction of the current, and your fingers curl around in the direction of the magnetic field. Now you can go back to this simple loop and figure out and go all the way around this little loop and do the right hand rule, and you'll see that in fact the magnetic field looks like that if you add it up all the way around, because the direction is changing all the way around. Okay, so here's just another drawing of the same thing, right? Your thumb is the current and your fingers are the field going around the wire carrying the current I. And furthermore, the magnetic field is stronger near the wire and it gets weaker as you move away from the wire. Okay, that's not too surprising. All forces, all fields are like that. Okay, that's a magnetic field from a current. Now, this electromagnetic induction, what is that? That is actually the basis for all generators. In other words, we get electric current, we get voltages in our home from a generator somewhere at a power plant. Okay? So if you take a magnetic field, the flux lines, that is to say all those field lines you saw coming out of the dipole, if you take that flux through a coil and you change the flux, you get a voltage. So in the lower left, for example, there's a bar magnet, there's a north pole. Here's a coil, actually it's a solenoid coil, connected to an ammeter, which measures current, or amps. Now, in the middle frame, if you move the dipole magnet into the solenoid, then the fluxes are the red lines. So the red lines are the magnetic field lines, and on the left there's no flux there. There's no magnetic field lines. In the middle, you've just shoved a lot of field lines into the solenoid, into the coil, and you get a large positive voltage or positive current going there. When you pull it out and the flux is going down, it's very high in the middle, and on the left-hand side you're pulling the magnet away, so the flux is on the way down, it'll generate a negative current, okay? And that's how you get your voltage or your current. So, changing magnetic field flux through a coil generates an electric field. The electric field makes a voltage, and the voltage gives you a current. And that's how our civilization works, okay? Every time you turn on a light, you're using this. Now in a lab, for example, here's a ammeter here on the right, and you connect the wires across the coil like this, and then you use some permanent magnets like you have one at least, and you can do the same thing as with your hands. You can run the magnet into this coil, and you can see a current, or a voltage actually, a voltage on the meter. Okay. So you can just do it with your hands. Now, finally, what about a force? See, electromagnetism, you know, when you put a charge somewhere, you have a force on it. And so we kind of saw that or tried to measure it. We saw the force of a charged PVC tube up against an aluminum can, and there was a force. I mean, that aluminum can really accelerated, so there was a force on it. So, with magnetism, there's also a force. And the force is on a current I, inside of a magnetic field B. So if you have a magnetic field somewhere, it could be the Earth's magnetic field, and you have a current in the field, then there's a force on that current right away. Okay, and the direction of the force is you put your fingers in the direction of the current, you flip them around so that your fingers now point in the direction of the magnetic field B, then your thumb is the force. Notice your thumb is perpendicular to both the current and the field. So the force law for magnetism is actually rather different. It's perpendicular to the current and the magnetic field, right? Again, you use your right hand, okay? So here's a three-dimensional drawing of it. You take I, you put here's I, B, and the force, the current I, and the magnetic field you're in, B, and the force. So you put your fingers in the direction of I, sweep them around into the direction of B, and your thumb is up, which is the force, okay? There's a vector formula for it there, but never mind the formula, okay? So now, this force actually is why motors work. Now here, on the left-hand side is Michael Faraday's first motor, all right? He used a bath of mercury here, which was conducting. In the bottom, he had a little magnet down there in the bottom, and then he had a wire hanging from the top here, and then he put a voltage between the mercury bath, and there's a little copper strip here, between the mercury bath and this post connected it here. So there's a current coming down this wire. And on the right hand, now, in our labs, we're not dealing with mercury, because now we know mercury is quite toxic, okay? So we don't have any mercury around, but we do have salt water. Salt water is also a conducting liquid, okay? So, in fact, if you take a saltwater bath, a magnet, that little red thing is a magnet, that could be one of our neodymium magnets, and a battery. And so now, the battery has a positive terminal, negative terminal, so the current goes out of the positive terminal through here, comes down here, and then the magnetic field lines, it's a dipole now, so there's some field lines that go straight up, and some of them arc to the right, and the ones that arc to the right pass at sort of like 90 degrees through the current that's coming down. So if you take I coming down and B going out at this point, the force on this wire will be out of the page, and so it'll come out and it'll actually circulate around in the salt water, circulate around the magnet. And that was the first motor. Now, that's not very efficient. There's not a lot of force. It's actually totally impractical in the sense that you couldn't use this thing for anything. But if you look at some of the motors today, for example, the motors in electric cars are really spectacular. They're like, probably 100 million times as strong and as efficient as this first motor. And that's actually quite typical of... So you can make your own, by the way. Here again is the saltwater bath, and here you can see the direction of the current is the gray arrows. And the current completes itself, by the way, by going through the salt water and then connecting to the negative terminal of the battery. So the salt water is a conducting liquid. So anyway, one of the TAs in your class made one of these a couple of years ago, I guess. It worked very nicely. It just kept on going around in a circle. Okay, an actual genuine motor. Okay, so now we can build another simple motor, and here it is. It's called a homopolar motor. It only uses one pole of the battery. I mean, like the North Pole, for example. It doesn't use both poles, so half the magnetic field is wasted here. On the right, on the left is a AA battery, and here's the neodymium magnet on the bottom. Okay, and so if you, on the figure on the right, the blue shows you the magnetic field lines. And just as we measured, just as you will measure, the magnetic field lines are the magnetic field of a dipole. Okay? And then the red wires coming out of the top of the battery, going around and coming down to connecting to the bottom, the negative terminal of the battery, because the magnet is also conducting, by the way. It's metal there, so you just have to touch it. And then there are two loops, one coming around on the right and one coming down on the left, and both connecting to the bottom. So the red and the diagram on the right is the current, okay, coming through the wire. Now, let's take one of the places where the current and the magnetic field cross. In fact, kind of up here in the upper right. So the current is down, magnetic field is to the right. So now if you're limber enough and use your right-hand rule, I crossed into B is a force at this point which is out of the page towards you. On the other side, it's into the page, away from you. So this wire has a force on it. Okay, it's a current inside a magnetic field, and there's a force on it. So it starts spinning around, actually spinning around clockwise, if you look at it from the top. That's a homopolar motor. And so now I kludged together one of these things. Here's my comment about safety in magnets here. Let's see now. I'm not sure which one. I'll do this one first here.
Okay, this is going to be a homopolar motor, and homo simply means one, so it's going to have only one pole of the magnet. And here's the magnet. It's the same thing. It's a neodymium permanent magnet, and there's enough iron in the metal of a AA battery here to hold the little magnet on there. Okay, and so. And it's also, this permanent magnet is also conducting, so it's not only magnetic, but it's conducting. So here's like the North Pole. This is the positive terminal of the battery and the negative terminal of the battery. Now, in the recorded lecture, there's a very nice drawing of the same thing, a AA battery and a wire that's very nicely circular and connecting. And this one, I just put this together to show you how badly you can do it, and it still works. So this is the piece of copper wire in your week 14 envelope. There's pure copper. There's nothing on it. It's just pure copper. And so, and then I put a loop here. I use the magnet to make this loop, so it fits right over the battery. I just use the battery as a mold, as a form to make this. And so this will go down, and this part will touch the magnet at the negative terminal of the battery. And then it goes around and it touches the top terminal of the battery. So, and this will just rest here. Okay, it may fall off and so on, but this is the positive terminal of the battery. So the current will flow when this touches that. The current will flow around here to the bottom, to the negative terminal of the battery, and it'll also flow around the other side. Okay, so the current out here, the current will be going down, and then the magnetic field, as you saw, the dipole field here, the dipole field will go up and turn around like this. It'll have a dipole field. So the magnetic field will be pointing in the direction in which the pen is pointing. So the force on the current carrying piece of copper will be the direction of the current crossed into the magnetic field, which is this way. And so it'll go down, and the right-hand rule here, fingers down, curled into the direction of the magnetic field, and your thumb is the force. So the force should be this way. The force should be this way. And consequently, on the other side, the force will be this way. So it should start to turn in this direction. Now, to be honest with you, I didn't actually check whether the North Pole's on the top or the bottom here. I assumed it was the North Pole on the top. If it's the South Pole on the top, it'll just turn the other direction. So we're not going to worry about that. Okay, I could check that. So now I'm going to connect the circuit. In other words, by connecting the top of the battery to the bottom of the battery, so current will be flowing down here. So let me do that. And so you can see this is not very pretty. I can make a much prettier thing up here and make a much better contact here, and maybe make another circle like this around the top. And I tried doing that, but I found it a little awkward, so I didn't do it. So this is just a very crude looking wire circuit. So here we go. Put it down here, put it on the top, and there you go. That's the motor. Okay, now you see it flipped off, right? It didn't stay there very long, and it flipped off again. Well, it's still making contact, so it's still going, but just barely going. But that is an electric motor. That's the basic principle of an electric motor here, right? And better built, it'll be more efficient, and so on, and whatnot. But that's an electric motor. And so if you were to engineer this, you would make a motor that can drive a car. All right. Now, this doesn't have very much power, but you can see the principle is all the same. Okay, that's the homopolar motor. I challenge you to do a good job of doing this, and also consider what grade level you're teaching and how your children would do this. Because in my opinion, I'm not a psychologist, I'm not a teacher, in my opinion, when kids see something go, like a motor, that's a big thrill. Okay? All right.
And here's another one. I think I'm silent here, just more images of this motor going. Okay. Now, if one were to make another loop at the top and way to connect it, you could make a rather nice motor that would just keep going for a long time. Okay. Now here's a rather stylistic version of the same thing. This is exactly the same thing. You know, the connection at the top is kind of idealized and so on. But if you had, for example, something, maybe an indentation in the top and some sharp point going down, you could make it stay there, and then it has to connect at the bottom here. So here's a drawing now. Here's a drawing, complete drawing of the battery and of this rather idealized copper loop going around. And then also the red lines are the field lines of a dipole, okay, dipole magnet. So you can see all the way along the copper current coming from the positive terminal all the way down to the negative terminal, B and the current I crossed at many points along here. So all along the right-hand side, the force is coming out of the page towards you. And the notation in physics for a vector, like an arrow coming out of the page, is a vector out of the page is a circle with a dot. It's like the tip of an arrow coming at you. And so the force is coming out all the way along this side. The force is coming out, and all the way along the other side, the force is going in. Okay, because because V cross B has the other sign. And so a vector going into the page is like a cross inside of a circle. It's like the tail of an arrow leaving you. So you can see the force acts, there's a force all the way along one side and all the way along the other side. And you see, it doesn't have to be very pretty. You can make a very pretty rectangle like this and make it much nicer and more efficient than mine. But even my crummy copper wire, you know, bent all over the place, still worked fine, right? So. Okay, so that's a homopolar motor. That's always worth doing. Even if you have trouble at it, just keep at it, okay? And I think it'll be just fine. You can do it. So now, you know, in this case, what spins around is the conductor, the current carrying conductor, the copper wire. You can also, actually, if you have say a bolt or you can put the magnet on the end of the bolt. On the end of a screw, a large screw or a nail even, and then which is also magnetic, a little iron in it, and it'll hang on to the bottom of a battery, and then the wire goes all the way around and touches the magnet at the bottom, and then what spins then is the magnet spins. The wire stays fixed, the wire is fixed, and the magnet spins around, okay? So that's the same thing, actually. I tried this. There's a drawing of it on the right here, okay, where B and I crosses B, so you get a force, the same way as the homopolar motor. And I tried this, but it didn't work very well. I think the bolt I have on hand had rather poor conductivity, I think, okay, so it didn't work very well. Okay, here's the same thing, by the way. You know, if you have a bigger battery, for example, you can see the magnet on the bottom of the screw, and you just have to connect with a wire the negative terminal of the battery to the magnet, and then it starts spinning, and the magnet spins around, and this bolt spins around too, okay? Now, let's get closer to an actual useful motor, okay, like with the commutator. There's a photograph here of a coil, many turns, maybe 20 turns of copper wire, and then the wire comes out and is held on a couple of paper clips, okay, sticking up, and there's a magnet. This gray thing, dark thing is actually, square thing is actually a magnet. It's not a strong magnet, and a 9-volt battery here. And so, in fact, now, and now you can see you put the battery across these two posts, these two paper clips, and the current flows from the right-hand side into the coil. It goes around the coil, so it makes a dipole field. from a current, and it comes back out to the battery. So you can see that the red arrows are the direction of the current, and the blue arrows are the dipole field from the magnet. So you also have an I cross B. I mean, all the way along here, I and B make an angle with respect to each other. And so there's a force. So this thing starts spinning around. And so it's a coil. It's a coil inside of a magnetic field. This is now closer to what a real motor is like. Now at the end, there are 5 videos, and you can look at all 5 actually. A couple of them are actually making motors like this, okay? And so now tonight, you see, I went ahead and I started to did I have 2 copies of this? Okay, here we go. I started to make one of these, okay?
Okay, this is a coil for a motor. And so I coiled up the enamel-covered copper wire, so it looks not quite as pure copper. So this is an enamel, so this is really insulated wire. So I've done only 6 turns, okay? I think you can get 6 turns. And here are the 2 ends. And then I put a small straw. There's a small straw from week 12, I think, or 13 in here. I used a small straw instead of the large straw. And then put it right through, you know, with 3 turns on this side, 3 turns on that side, and so on. So we're going to make our motor like this, okay? But in order to make the current pass through the coil, we have to make an electrical connection to these 2. And they're covered with enamel. So I'd have a little scraper here, and I'm going to scrape the enamel off. That's what I'm going to do now. And it's a bit of a chore, okay? A bit of a chore to do that. But I want to make sure that it's scraped down to the bare copper. I'm not doing a very good job here. And I should have thought of this ahead of time, because I could have gotten a piece of sandpaper and just sanded it off before making the coil. Before making the coil. Oh boy. Yeah. And then it would have been all off and very clean, and make sure that it make good contact. Okay. That's one side. Then I'm going to do the other side. So you can stop now if you want to. One could also use wire with insulation on it, right? Plastic insulation on it. And that might actually be better. You don't have to mess with scraping off enamel. It makes the rotor heavier because it has a lot of plastic covering on it. So there you go. Okay, so I'll put these down to here and down here, and then I'll attach them to the copper tape. And copper tape will make the commutator. Okay, so let's do that later. Okay, this is a coil for a motor.
Okay, so I think what I did is I pulled this in twice, unfortunately. So let's go on to this one here. I'm trying to make it work.
Okay, so here is the beginnings of a motor with a coil, and then 2 conductors coming out on the ends of the wire come out here, and I've scraped off. I tried to use the copper tape, but it didn't work. And so here's a battery, a magnet here. And then these are just a couple of paper clips which I pushed into the sides here. And they simply are meant to hold this up. So, so the straw will sit on here like this. And so you can see it's not beautiful, but it kind of looks like something like a motor, okay? And it's actually not even very sturdy. But anyway, there you go. Now, the problem I'm having is connecting the battery across these 2 wires. There should be when I connect it, there should be oops, it was smoking. It was smoking. So it did connect, but okay, but it's not working. It's not working. And the whole problem I'm sure, is the connection here and here. So, this, like first attempt, and it requires another attempt. And I think the best thing is to have a longer wire coming out here, and so on. But anyway, but that's the idea. That's the idea. This was trying to put a commutator here was a little bit too tricky, and then this is an ohm meter. It measures the resistance. We want the resistance between here and here to be basically 0. So you can see if I just touch the 2, it goes down to basically, well, it's not 0 resistance, but it should be very small resistance. Good gosh, it's not. I wonder whether the battery, see, it's 0.6, 0.5, 0.4 ohms, right? And so it should be the same across here and here. And you can see it's, well, all right, so it's 4.67. See, there's too much resistance in here. And I think that's because I did not scrape. There's too much resistance across these 2 points. Even an ohm is too much resistance here. So that's the problem, is I didn't scrape these well enough. Didn't do a good enough job on these 2 contacts, okay? But when it does, and if I were to work on this for another half hour, I could get it to go. But generally speaking, this kind of a motor works very, very well. It just goes like that. Okay, when you put the current on there, you get the same force that we had on the homopolar motor, and it just spins around like that, makes a rather nice motor. Okay, so sorry this didn't work. I can't expect you to do what I cannot do, but give it a crack. Do what you can here. And with this much wire, I think maybe it might be enough. Okay.
Okay, so at the end we'll see there's some videos of people who do this quite easily, okay, and maybe I should have followed one of those videos. But there are many techniques for making motors or rather even using magnets, using just electromagnets. And so here's a start of a motor with electromagnets instead of permanent magnets, and you have a glass tube and maybe a nail, so the spins will hardly any friction, and there's a cork. And then here's all of the wiring, okay. The wiring goes around one nail, makes the north pole there, goes over to the commutator, called brushes here, the commutator, and goes through the nail and makes a north and south pole there, and then continues on through the other nail on the other side, makes a south pole at the top, and then all you have to do is connect the battery across these 2 terminals, and you have a complete motor with actually no magnets in it at all, but just electromagnets. So there are many things to do. So now actually let me finish up here. Activities, what I want you to do is measure the magnetic field of your permanent magnet and try to do a good job of that. Make a sketch that you're proud to show, and then make a homopolar motor with a spinning current wire, okay? And then if you have a nail or a screw, try to make a homopolar motor with a spinning magnet, and this may take a little time and patience, okay? And then try, if you can, by making a real coil motor with a commutator by scraping off half the enamel. Now, don't follow my directions on this. There are 5 websites here. The first 3 are PFET, which are simulations, and actually, not bad actually, okay? You can do the magnet compass measurements and move the compass all around and change the strength of it and so on. You can do Faraday's law here in the second simulation, and also Faraday's law, the more sophisticated, and so on. And then these next 2 YouTubes are people making small magnets. The second one is actually quite nice, very simple magnets. I think it starts with a D battery and rather than a AA battery and so on. And then the one in front of it is somebody else made a magnet. It's sometimes not so simple, but it's quite nice. So I suggest you look through these simulations, okay, and also these 2 YouTubes to see and get an idea and go from there, okay? I think that's the best thing to do. Okay, so I'll see you at 3:20 Monday, okay, in the afternoon. Any questions you have, I may work some more on this motor to see if I can get it to go, although I realized I only put so much wire in each envelope for week 14, so you're kind of running out of wire, but maybe I'll undo the wire and try again. Okay, thank you. See you at 3:20.